is revealed through X-ray crystallography and cryo-electron microscopy. Using this painstaking method, only 17% of the roughly 25,000 human proteins have been decoded. In the vast space of human disease, without the 3D structure of most human proteins, computer-aided drug discovery is limited. Just this year, the researchers of AlphaFold and RosettaNet taught their AIs to predict the 3D shape of proteins from just their amino acid sequences. Overnight, DeepMind decoded over 20,000 human proteins. The tedious process of decoding a protein is turbocharged by an AI model. There are hundreds of millions of animal, plant, and bacterial proteins that can now be decoded. Meanwhile, AI models are now able to learn characteristics of known effective chemicals and generate other potentially effective novel chemicals. Millions more potentially effective chemicals meet hundreds of thousands more protein structures, opening up a gigantic, unexplored space of new opportunities. The opportunity space has increased many orders of magnitude, 1,000,000-fold. This has created overnight a massive molecular simulation bottleneck. How do we get the million X leap to engage this opportunity? Physics ML might be the answer. Researchers at Nvidia and Caltech used physics ML methods to teach a graph neural network to replace the expensive quantum calculations of atomic forces in a molecular simulation. OrbNet predicted Schrödinger's equation. The result is a 1,000-fold increase in simulation performance. Entos is a super cool company focused on using machine learning and computing to revolutionize drug discovery. This is a simulation of HSP90, a chaperone protein that helps other proteins fold properly. You're watching something amazing. This video shows a simulation of the chemical reaction that is happening between the HSP90 protein and a candidate drug. The candidate drug is forming a chemical bond with an amino acid of the protein. These chemical reactions are rare events, so we have to simulate at very long timescales. And because electrostatic simulations cannot model the atomic bond, quantum methods are needed to compute free energy of the reaction. This simulation took 3 hours on one GPU. Without the OrbNet physics ML, it would have taken over 3 months. The future of drug discovery is computational end-to-end. Modeling the disease pathway, the genes involved, the drug-target interactions, and the off-target interactions. With the confluence of million X acceleration, ML for protein and chemical structure prediction, and physics ML simulation approaches, we are witnessing the dawn of the biology revolution. For climate science, we may finally have a way to simulate the Earth's climate 10, 20, or 30 years from now, predict the regional impact of climate change, and take action to mitigate and adapt before it's too late. Severe droughts are happening around the world. This is not caused by the lack of rain, but higher evaporation from rising temperatures. The dryness is also causing more wildfires. Predicting climate change, so to develop strategies to mitigate and adapt, is arguably one of the greatest challenges facing society today. We don't currently have the ability to accurately predict the climate decades out. Although much is known about the physics, the scale of the simulation is daunting. Climate simulation is much harder than weather simulation, which largely models atmospheric physics, and the accuracy of the model can be validated every few days. Long-term climate prediction must model the physics of Earth's atmosphere, oceans and waters, ice, the lands, and human activities, and all of their interplay. Further, simulation resolutions of 1 to 10 meters are needed to incorporate effects like low atmospheric clouds that reflect sun's radiation back to space. Ignoring these contributions accumulate to significant error in the long-term predictions. This is 10 to 100,000 times higher resolution than any weather simulation today. There are no computers big enough that we can build. We need a computer science breakthrough. Today, we're announcing Nvidia Modulus, a framework for developing physics ML models. Train physics ML models using governing physics and data from principled models and observations. Modulus has been optimized to train on multi-GPU and multi-node. The resulting model can emulate physics 1,000, 100,000 times faster than simulation. With Modulus, scientists will be able to create digital twins to better understand large systems like never before. One important problem we can apply Modulus to solve is climate science. Climate change is reshaping the world. The largest reservoirs in the US are at their lowest level in 2 decades, some 150 feet below where they were. The combination of accelerated computing, physics ML, and giant computer systems can give us a 1,000,000x leap and give us a shot. We will use principled physics models and observed data to teach AI to predict climate in super real time. We can create a digital twin of the Earth that runs continuously to predict the future, calibrating and improving its predictions with observed data, and predict again. Researchers trained a physics ML model using atmospheric data from Era 5 of ECMWF. The model took 4 hours to train on 128 A100 GPUs. The trained model can predict hurricane severity and path at 30-kilometer spatial resolution. 7 days of prediction takes only a quarter of a second on a GPU. That's 100,000 times faster than simulation. Hopefully, in a couple of years, data will stream into a digital twin of Earth, running in Omniverse. An ensemble of physics ML models will predict the climate. Let's talk about Omniverse. The internet changed everything is surely an understatement. We are always connected now. The internet is essentially a digital overlay on the world. The overlay is largely 2D information, text, voice, images, video. But that's about to change. We now have the technology to create new 3D virtual worlds or model our physical world. These virtual worlds will obey the laws of physics, or not. There can be AI or friends with you. We will jump from one world to another, like we do on the web with hypertext. This new world will be much larger than the physical world. We will buy and own 3D things, like we buy 2D songs and books today. We will buy, own, sell homes, furniture, cars, luxury goods, and art in this world. Creators will make more things in virtual worlds than they do in the physical world. We built Omniverse for builders of these virtual worlds. Some worlds will be built for gathering and games, but a great many will be built by scientists, creators, and companies. Virtual worlds will crop up like websites today. Omniverse is very different than a game engine. Omniverse is designed to be data center scale, and hopefully someday, planetary scale. The portal of Omniverse is USD, Universal Scene Description, essentially a digital wormhole that connects people and computers to Omniverse, and for one Omniverse world to connect to another. USD is to Omniverse what HTML is to websites. Omniverse is futuristic. Omniverse can connect design worlds. Things created in the Adobe world can be connected to those in the Autodesk world through Omniverse, enabling designers to collaborate in a shared space. Changes by a designer in one world are updated for all connected designers, essentially like a cloud shared document for 3D design. Omniverse will revolutionize how the 40 million 3D designers in the world collaborate. Companies can build virtual factories and operate them with virtual robots in Omniverse. The virtual factories and robots are the digital twins of their physical replica. The physical version is the replica of the digital, since they're produced from the digital original. Omniverse digital twins are where we will design, train, and continuously monitor robotics factories and buildings, warehouses, and cars of the future. Let me show you some of the fundamental technologies that make Omniverse possible. We are releasing a big update to Omniverse today with some exciting new features. Showroom, an Omniverse app for demos and samples that showcases core Omniverse technology, graphics, physics, materials, and AI. Farm, a systems layer that orchestrates the processing of batch jobs across multiple systems, workstations, servers, bare metal, or virtualized. Farm can be used for batch rendering, synthetic data generation for AI, or distributed computing. Omniverse AR streams graphics to phones or AR glasses. Omniverse VR is the world's first full-frame interactive ray-traced VR. Since launch last year, Omniverse has been downloaded 70,000 times by designers in 500 companies. Along with us, the community, companies, tool providers are building Omniverse connectors. There are 14 available now and 15 more coming soon. Bentley announced that iTwin with Omniverse is now in early access. Bentley is not just connecting the Omniverse, they're building their digital platform on it. Bentley is used by 90% of engineering firms and has nearly 2 million users of Bentley iTwin. Heat recovery steam generators, or HRSG, converts the hot gas out of a combustion turbine into steam, which drives a steam turbine to generate electricity. Corrosion is certain, so inspection and maintenance are needed. Siemens Energy estimates that by predicting corrosion accurately, they can reduce inspection during regular maintenance and unplanned downtime by 70%. Reducing the industry 5 to 7 days can save nearly $2 billion a year. HRSG corrosion is a multi-physics problem with a combination of flow characteristics, water chemistry, and operating conditions. Using Nvidia Modulus, the physics ML framework, and Omniverse, we've created a digital twin platform with Siemens. Let's take a look.
This massive heat recovery steam generator uses hot gas exhaust to convert water in the pipes into steam for the turbines. Predicting corrosion to avoid downtime is challenging. Reduced order models aren't extremely accurate, and full simulation takes expertise and time. Siemens Energy is developing a digital twin with Nvidia Modulus for the multi-phase turbulent flow. With point cloud data to train a physics-based AI model, they can infer high-fidelity flow shown by the streamlines in seconds. This could reduce downtime by 70%, saving the industry $1.7 billion a year.
BMW produces one vehicle per minute, each with roughly 25,000 parts. There are 5 million parts on the factory floor at any time. At GTC Spring, BMW showed us how they're building a digital twin of their Regensburg factory. They have since expanded to 3 other factories, totaling 10 million square meters. Their engineers are also using Isaac Gym, built on Omniverse, to teach their robots new skills. Let's take a look at the digital twin factories that BMW is building.
BMW has continued building on the momentum of their Factory of the Future initiative we showed you earlier this year. On average, they produce 1 new vehicle every minute, expanding the initiative to now include digital twin projects at 3 additional factories, which total more than 6 million square meters. Meeting BMW's demands for continuous improvement and innovation requires simulation of complex production scenarios to speed output, increase agility, and optimize efficiency everywhere. Nvidia Omniverse introduces new simulation capabilities everywhere BMW needs to make critical decisions and introduce automation. BMW and their partners have also been connecting new users and tools to expand the Omniverse ecosystem. Spanning every aspect of the BMW Factory of the Future, Omniverse allows BMW to collaborate and simulate from the entire plant level down to comprehensive engineering detail.
Ericsson is building a digital twin of a whole city to configure, operate, and continuously optimize their fleet of 5G antennas and radios. This is a really great story. Take a look.
There are 15 million 5G microcells and towers planned for global deployment in the next 5 years. Ericsson is using Nvidia Omniverse to build digital twin environments to help determine how to place and configure each of their sites for the best coverage and network performance. In Omniverse, Ericsson builds city-scale models that are physically accurate down to the materials of the buildings, vegetation, and foliage. Then, wireless network components are added including the precise location, height, and antenna pattern of each transmitter. Ericsson built a custom Omniverse extension, enabling them to integrate radio propagation data and leverage Omniverse's RTX accelerated ray tracing to quickly visualize and calculate the quality of the signal at every point in the city. Because Omniverse materials are physically accurate, the intensity of reflections are precisely determined. Antenna beamforming and signal paths can be accurately simulated and visualized. In the simulations, the lobes signify transmitter antenna beamforming and the straight lines are signal paths. The colors of the signal paths denote strength in decibels and data throughput, from blue is the weakest to red is the strongest. Visualization is a critical capability for Ericsson. With Omniverse VR, network engineers can virtually explore any part of the model, teleporting to any location, anywhere in the world, at 1-to-1 scale. As they tune the network for optimal performance or identify path disruptions, they can literally see the effects of their adjustments in real time, things which aren't visible in real life. In Omniverse, Ericsson can perform true-to-reality remote simulation of entire 5G networks, enabling them to design more efficient and reliable networks, conduct remote field trials, and speed up deployments.
Someday, that fleet of antennas will use AI to learn the best beamforming and signal strengths to optimize the quality of service and throughput in the city while conserving energy. Omniverse, as you could see, is a foundational platform for digital twin virtual worlds, where AI systems are created. Let's talk about building AI models and systems. Graphs are the native format, the most natural data structure of the world's data. Whereas CNNs learn from spatial data and RNNs learn sequences, graph neural networks can learn relationships. How molecules connect to each other in a protein, how people are connected in a social graph, how roads are connected to town cities, all can be described as a graph. Deep Graph Library, DGL, is a Python library built to implement graph neural networks on top of existing deep learning frameworks. We're working with the DGL community to accelerate GNN processing, like we have with CNNs, RNNs, and transformers. From constructing the graph to sampling subgraphs and projecting graphs into a DNN framework, we are accelerating the workflow so that developers can train and inference graphs with billions and trillions of edges. GNNs are the new go-to models for financial services, drug discovery, digital biology, and cybersecurity. Our early graph engagement partners have seen excellent results. PayPal significantly improved their collusion fraud detection. Amazon used it to improve Amazon search and reduce abuse and fraudulent sellers and buyers. They processed graph sizes impossible before. Pinterest scaled search and recommendations to 500 million users. We will have early access in December. Transformers are models that can learn sequence patterns in parallel. This breakthrough sped up language model training dramatically, which led to self-supervised language learning. No longer limited by human data labeling, giant self-supervised transformers benefit from the troves of digital knowledge on the internet. The recent breakthrough of large language models is one of the great achievements in computer science. There's exciting work being done in self-supervised multimodal learning and models that can do tasks that has never been trained on, called zero-shot learning. 10 new models were announced just last year alone. Training large language models is not for the faint of heart. $100 million systems, training trillion parameter models on petabytes of data for months required conviction, deep expertise, and an optimized stack. We created Nemo Megatron, a framework dedicated to training speech and language models of billions and trillion parameters. It is optimized to scale out to gigantic systems and sustain the highest computation efficiency. Our researchers trained GPT-3 on Nvidia's 500-node Selene DGX SuperPod in 11 days. And together with Microsoft, trained the Megatron MT-NLG 530 billion parameter model in 6 weeks. With Nemo Megatron, any company can train state-of-the-art large language models. Once trained, how do we run these large language models? Inference response time has to be sufficiently fast to be useful. On a high-end dual Xeon Platinum CPU server, inferencing Megatron 530B takes over a minute. For many applications, that's basically unusable. GPU accelerating these models is also challenging because the model sizes require much more than a frame buffer size of a GPU. GPT-3, with 175 billion parameters, needs at least 350 gigabytes of memory. Megatron, with 530 billion parameters, needs over 1 terabyte of memory. So we created the world's first distributed inferencing engine. Nvidia Triton now does distributed processing across multiple GPUs and multiple nodes. GPT-3 will fit easily on an 8 GPU server. Megatron 530B will distribute across 2 DGX systems. The performance is incredible. From over a minute to half a second. The capability and implication of large language models are profound. LLMs can answer deep domain questions, comprehend and summarize complex documents, translate languages, write stories, write computer software, understand intent, be trained without supervision, are zero shot, meaning that they can perform tasks without being trained on any examples. LLMs are pre-trained on general knowledge and can be retrained to effectively serve new domains. There are 20 or 30 languages that represent 80% of the world's population. There's easily 100 industrial or science domains, and within them, plenty of use cases. Sweden is working on digitizing its history. Samsung is building a smart speaker for the over 200 million Portuguese speakers in South America. VinBrain is training a Vietnamese large language model for healthcare. JD is building an LLM for their e-commerce services to engage their 500 million customers. Rakuten is building a Japanese LLM for their digital services. ServiceNow is building an IT help desk chatbot. And Xiaomi, the world's largest phone maker, is building an AI assistant. Customizing large language models for new languages and domains is likely the largest supercomputing application ever to come along. There are many AI models that are now mature and industrialized for broad enterprise use. Computer vision, speech recognition, recommender systems, graphs and trees, time series models, generative models, variable encoders, and large language models. There are excellent applications and uses of AI in leading companies across the world's industries. It's great to see them present their work at GTC. Be sure to go watch their talks. There are now 25,000 companies running AI on Nvidia. Financial companies are looking to reduce fraud on over 1 billion credit card purchases a day, loss that cost the companies and consumers over $35 billion a year. Customer and contact centers are overwhelmed. There are over 500 million calls a day. This is a $20 billion industry. And of course, e-commerce product service recommendations for what is soon to be a $10 trillion industry. For all companies, automation is vital to growth, and AI is the most powerful automation technology we have ever known. Video conferencing is one of the most important apps for most of us today. We're doing 15 billion meeting minutes a day. Microsoft has over 200 million active users. We're delighted to work with Microsoft to develop live captioning across 28 languages. This is an invaluable feature for those who are deaf or have hearing difficulties. Every captioning session is personalized for each meeting to understand names of people and specific jargon. Video conferencing technology is going to advance very fast. Going forward, a great deal more AI will be infused. In addition to background and noise removal, there will be AI for all kinds of amazing things: language translation, eye contact, relighting, and much more. Let's talk about inference. AI is a new way to write software, and inference is running the software written by AI. Inferencing is challenging on multiple dimensions. The computation intensity of the networks is high, but that's just the start. AI is data-driven, so the movement of data, the pre-processing and post-processing of data, all play into its performance. Nvidia's CUDA GPU architecture shines at processing this end-to-end pipeline. AI applications have different requirements. Response time, batch throughput, continuous streaming. Different use cases have different models, and deep learning architectures are really complex. There are different frameworks. There are different machine learning platforms. There are different platforms with different operating environments, from cloud to enterprise to edge to embedded. There are different confidentiality, security, functional safety, and reliability requirements. And the world has a large installed base of different CPUs and GPUs, each with different capabilities and performance characteristics. The combination of all those requirements is gigantic. Inferencing is arguably one of the most technically challenging runtime engines the world has ever seen. Today, we're making the biggest release of inference tools ever. First, NVIDIA's TensorRT compiler has been integrated natively into TensorFlow and PyTorch. Many developers inference directly from the frameworks. It's easy, it always works, but it's slow. Now with one line of code, machine learning developers can get a 3 times boost without lifting a finger. Just one line of code. Tree models are ubiquitous, especially in finance. It is naturally explainable, and new predictive features can be added on without fear of regressions. Today, we're announcing that our Triton Inference Server will do inferencing on DL as well as ML models. The performance is fantastic and game-changing. Here's an example on the IEEE fraud detection dataset. The goal is to improve detection rate while responding in time to block the transaction. In this chart, that's staying to the right of the red line, which marks 1.5 milliseconds, the longest allowable processing time. For small trees, both CPUs and GPUs can do so. However, with large trees needed for better detection rates, inference time remains under 1.5 milliseconds for a GPU, while a CPU now takes 3.5 milliseconds, way too long to block the transaction. With this release, we open NVIDIA GPUs to the world of classical ML inferencing. Now with one inference platform, Triton lets you inference DL and ML on GPUs and CPUs, announcing a major upgrade to our Triton Inference Server. Inference on all models, any framework, multiple query types, ML and DL, for all platforms, cloud, on-prem, edge, and embedded, multi-GPU, multi-node, on CUDA, x86, and ARM. One engine, NVIDIA Triton, for all inference workloads. The performance of Triton is spectacular across the board, from imaging to speech AI, natural language processing, recommenders, and reinforcement learning. For CSPs, Triton drives up the utilization and throughput of their infrastructure, freeing capacity for new growth. For users, Triton drives up throughput while reducing cost. This is one of the major benefits of the NVIDIA platform. With our full stack optimization and rich ecosystems, customers enjoy boosts in performance and new functionality throughout the entire life of use. Years after purchase, our chips keep getting faster and better. The more you buy, the more you save. Every company in every industry is looking to increase automation. To automate, we need to program computers to recognize patterns and execute a task repeatedly and safely. But the world is unstructured. The range of tasks humans perform in an infinite range of circumstances is impossible to describe in programs and rules. Advances in AI have opened new opportunities to automate tasks unimaginable before. In computer industry parlance, the edge is where computers touch the world. A large number of edge applications today can be processed in the cloud. For example, people using phones connected to cloud services. For many edge applications, transit to the cloud is not possible for response time, data security, or reliability reasons, or the practicality of data transport costs for continuous high-speed sensing. Edge applications are essentially robotic applications. They perform similar tasks, under similar requirements as self-driving cars. The unifying concept of edge computing is the need to process some combination of sensors, high-speed I/O, data processing, signal and physics processing, AI inferencing, and computer graphics. This is basically the robotics pipeline. It must be processed in real time. Processing time translates to safety, cost, capacity, and ultimately usability. So how do you build the AI applications that process the robotics pipeline? We created the Nvidia Unified Computing Framework. It lets us compose containers and microservices into a fast pipeline by chaining the processing of dedicated accelerators, the CUDA GPU, Tensor Core AI, RTX graphics, networking, security, and fast I/O. UCF lets you build AI applications that can process the robotics pipeline. UCF can create applications that run in data center or embedded systems. Buildings, warehouses, factories, farms, and roads will be able to sense in the future. Metropolis is our video processing and analytics platform. From streaming video, it can detect, track, count, infer 3D pose, and even reconstruct full 3D scenes in the future. We support cameras today, but it's an easy extension with UCF to support LiDAR, depth sensors, imaging radars, ultrasonics, and infrared. Metropolis is full stack and open, like all of our platforms. Customers can use Metropolis application as is or customize our graph. The stack can integrate third-party 5G radio, accelerated by our Aerial CUDA Phi. And Nvidia certified edge computing systems are available from every computer maker. Mavenir, the leader in software-defined 5G solutions, builds 5G core and virtualized radio access networks. They use Metropolis platform to create a fully optimized construction kit to do AI on 5G for industrial applications in factories, plants, public spaces, farms, and places where IT is limited. Mavage AI will be available to early access customers in Q1. The combination of rich sensors, computing, and AI at the edge will inspire a wave of new ideas, applications that are simply not possible today. Here is an example of work that we're doing with Verizon.
Volumetric video can offer exciting entertainment experiences. Here, Yahoo Riot Studios places live-action rugby footage in a variety of settings. Traditional edge compute architectures cannot process 3D volumetric data from 50-plus high-resolution cameras in real time. Verizon adopted a breakthrough approach which bypasses the CPU by using Magnum I/O to write video streams 10 times faster and process up to 250 terabytes of video per half hour. In the future, low-latency 5G, edge computing, and Nvidia GPU acceleration will enable Verizon to open new options for putting you in the game.
In this chapter, I've shown you how we train new models, graph neural networks, and large language models, and how Triton is one engine for all inference workloads. And using UCF, how you can compose these models into edge applications. Our platform is full stack and open, runs from the cloud, on-prem, to edge and embedded. With partners across the industry, we've built a rich ecosystem that connects NVIDIA AI into whatever IT infrastructure, software platform, workflow, or integrator you choose. Still, there remains a great deal of engineering to stand up these stacks. For that last mile, we're partnering with Equinix to pre-install and integrate NVIDIA AI into their data centers around the world. We're making it easy for enterprises to test drive their workload. And when you're ready to scale out, the full recipe is available to our network of partners to help you do it at Equinix, your own data center, or anywhere else. We call this Launchpad. You will find Launchpads all over the world, in Silicon Valley, Dallas, Washington, D.C., London, Paris, Amsterdam, Frankfurt, Singapore, and Tokyo. If there are other locations you would like a Launchpad, let us know. In the near future, there will be billions of robots to help us do things. Some will be physical robots. Most will be digital, virtual robots. Some virtual robots will be fully autonomous, others semi-autonomous, or even teleoperated. That is to say, with human in the loop. Maxine is our avatar platform. our virtual robots platform. We've been showing you pieces of our technology for some time. Today, I'm going to put all the pieces together. Maxine can be autonomous or teleoperated, realistic or artistic. Maxine can be used for a broad range of applications. For example, customer service, live, on the web, or in Omniverse. It can be used for video conferencing, or for animating game characters, or be integrated into a robot. The fundamental technologies of Maxine are just becoming possible. Computer vision, neural graphics, animation, speech AI, dialogue manager, natural language understanding, recommenders. These are foundational technologies we've been talking about for some time. This was pretty much impossible 5 years ago, and barely so today. First, speech AI. Today we're announcing the public release of Nvidia Riva Neuro Speech AI. This is the input-output of Maxine. We've dedicated significant R&D and built DGX SuperPods to make Riva possible. Riva speaks English, but recognizes 7 languages: English, Spanish, German, French, Japanese, Mandarin, and Russian. Riva will speak more languages in the future. Riva can close caption, translate, summarize, answer questions, and understand intent. Riva's accuracy is world-class, and the response time is unrivaled. And with only 30 minutes of training, Riva can be tuned to a specific voice. For example, one of a brand ambassador of your company. Riva can be fine-tuned for vocal pitch, duration, and energy of human-like expressiveness. Riva can be deployed in any cloud or at the edge. Early customers have seen excellent results.
The formulation of a problem is often more essential than its solution, which may be merely a matter of mathematical or experimental skill.
To raise new questions, new possibilities, to regard old problems from a new angle requires creative imagination and marks real advances in science.
This is a simplified diagram of Maxine's UCF graph, Unified Computing Framework. The Maxine Compute Graph consists of video, audio, graphics, and I/O processing. AI models include vision, speech, animation, language, recommenders. Maxine runs Nvidia AI on EGX servers and Omniverse on RTX servers. And all of it has to be interactive. Let's take a look.
Hi, welcome to Shannon's Cafe. How can I help you?
Can I have a cheeseburger with a side of onion rings, please?
Would you be interested in our popular toppings for cheeseburger like bacon and fried onions?
Yeah, let's do it.
Done. Added cheeseburger with bacon and fried onions. What else?
What protein options do you have?
We have multiple options. I recommend the double protein burger. Would you like that?
Do you have any vegetarian options?
I can get you a black bean patty instead. Would you like that?
Sure.
This is a Metropolis application. We call it Tokyo, a talking kiosk. The little animated robot is making eye contact and tracks the customers. From speech recognition to natural language dialogue manager that infers intent and actions.
Do you have any sides?
We have these 3 vegetarian items. French fries, onion rings.
To recommendation to natural speech, Tokyo responds in about 2 seconds. Very interactive. That was Maxine in autonomous and artistic mode. What if you would like to use Maxine in a teleoperated and realistic mode? This would be useful for customer service or video conferencing. Let's take a look.
NVIDIA Maxine is a remarkable innovation, one built to advance how we collaborate in this brand new online world of ours. With Maxine, you can speak several languages. Alles auf einmal.
Riva converts the text to speech in those languages. Omniverse takes over and converts the speech to 3D facial animation. Alex's German, French, and Spanish-speaking avatars are streamed simultaneously. Depending on which version of Alex's avatar you choose, she will speak to you in that language.
与大家更好地分享你的想法。Eye contact is critical to engaging your audience. Maxine keeps my eyes on you even when they're looking down at the script.
In this case, Maxine uses computer vision to track Alex's face and recognize her expressions. The 3D animation animates a virtual but realistic avatar of Alex.
You're actually not looking at me, but rather a portrait that Maxine brings to life. From a cafe that filled with noise that would normally drown me out, like this.
Let's talk about robots. Future medical instruments will become robotic. Recent advances in AI, physics ML, ray tracing, and the computing advance we've spoken about will also revolutionize medical instruments. The algorithms will be reimagined by AI. The instrument will be reinvented by edge computing architectures. The business models will be revolutionized as instrument sales will be replaced by medical device software as a service solutions. These dynamics are great for the patients, for the hospitals, and for the instrument makers of this $200 billion industry. The industry needs a software-defined imaging platform to build this future on, just as the auto industry needed a software-defined AV platform. Today, we're announcing Nvidia Clara Holoscan, a software-defined programmable imaging platform. Holoscan is the culmination of many years of planning. It takes all of Nvidia's technology to make Holoscan. The last two pieces of the puzzle are just coming online. Unified computing framework that I've described, and a new chip, Orin, a super fast sensor processing robotics chip. The base Holoscan platform consists of Orin and CX7. Orin can process the entire robotics pipeline, sensors, physics, AI, imaging, and graphics in a single chip. 12 ARM CPUs, 5.2 teraflops of FP32, 250 TOPS of AI, 740 gigabits per second, nearly a terabit per second of high-speed I/O to connect sensors. You can optionally add an A6000 ampere GPU and get another 39 teraflops of FP32 and over 600 TOPS of AI inference. With Clara Holoscan UCF, instrument makers have a development platform to build real-time applications that connect these powerful engines. The Holoscan platform is open. Third parties can build upon Holoscan's interfaces and APIs. Researchers can do great new science, and instrument makers can integrate Holoscan into their solutions. We are delighted that AJA Video Systems, Kaya Instruments, Verisonics, and Us for Us are building front-end sensors to support Clara Holoscan. Holoscan applications can be deployed fully in instrument, in the hospital's data center, or a mixture of both. This allows companies to develop applications that require more computing than is in the device, or to upgrade the installed base of devices years after deployment. Nvidia Clara Holoscan is a full-stack open platform for next-generation software-defined instruments. Holoscan is our third robotics platform. We've got some great updates on our other two, Isaac and Drive. The robotics industry is growing incredibly. Our Isaac ecosystem is now over 700 companies and partners. That number has grown 5 times in the last 4 years. AMRs, or autonomous mobile robots, are being deployed in giant warehouses to handle the incredible growth of e-commerce fulfillment. Cleaning robots, restaurant and retail automation robots, last-mile delivery robots, moving telepresence robots are all being worked on. A robot perceives the environment, reasons about where it is and where it needs to go, what it needs to do, and then develops a plan to do it. There are 3 interconnected work streams in building a robotic system. First, train the robot's AI models to perceive. For training, we have NVIDIA AI and DGX. Second, in a simulator, train the robot to manipulate or navigate. For simulation, we have Isaac Sim on Omniverse running on RTX. The Isaac Sim Omniverse simulation will also serve as the digital twin of the robot when deployed. Third, operate the robot in the environment. Here, Isaac, running on AGX, does the perception, localization, mapping, and planning, or otherwise, the robotics pipeline in real time. If the robots are connected over 5G and orchestrated from a central server in the warehouse, we would operate the Isaac stack on EGX. So DGX, RTX, EGX, and AGX systems and their appropriate software stacks make up the end-to-end machine learning loop. Isaac is a full stack and open platform. Isaac now supports the ROS ecosystem, the large open source robotics community. ROS has 700,000 developers and is growing fast. The Isaac runtime can now be a node in the ROS framework. For example, to do object detection, segmentation, 3D post-estimation, visual odometry, or point cloud processing. All of that can be 10 times faster. Instantly, ROS developers get a giant boost in performance and benefit from the algorithms in Isaac. ROS developers can also import the ROS URDF robot definition format directly into Isaac Sim to simulate their robots. Isaac Sim is the most realistic robotics simulator ever created. It's built on Omniverse. Sensors are modeled, physics is simulated, environments are photorealistic, robots in simulation are running their actual stack, either SIL, software in the loop, or HIL, hardware in the loop. The robot is connected to an actual map. It really feels it's in the environment. The goal is for the robot to not know whether it is inside a simulation or the real world. We strive to minimize the sim-to-real domain gap. Training data is incredibly hard to create for robotics. Unlike cars on roads, the world of robots is far more random. Cars follow lanes and avoid other cars. Robots have no lanes and are designed to make contact. It is impossible to collect and label all the scenarios to train a robot. Isaac Sim Replicator is an engine to generate synthetic data to train robots. Replicator simulates the sensors, generate data that is automatically labeled, and with a domain randomization engine, creates rich and diverse training data sets. The ROS community will be supercharged end-to-end with Isaac Replicator, Isaac Sim on Omniverse, and Isaac ROS. Someday, everything that moves will be autonomous, either fully or mostly autonomous. By 2024, the vast majority of new EVs will have substantial AV capability. We are developing an end-to-end flow for building autonomous vehicles, as well as a full-stack in-car AV system and a global cloud map. Nvidia Drive is full-stack and an open AV platform. Customers can decide to use just our development flow, parts of our driving computer, connect to our cloud map, or partner with us end-to-end. We're working with companies building cars, SUVs, sports cars, trucks, vans, robo-taxis, and food delivery vehicles. Autonomous vehicles are robots, and the same three pillars of machine learning development apply. Training models with Nvidia AI on DGX, simulation and synthetic data generation with Drive Sim on Omniverse, and a real-time robotics pipeline with Drive AV on the Orin robotics chip. The first goal is to transform the data from surround sensors into a 4D world model. The left image is showing the surround cameras. The right image is the world model, essentially the mind of the car. With a high integrity and high precision world model, we use it to avoid obstacles, localize to a map, reason about the environment, and plan paths to reach our destination. It starts with the sensor and computing architecture of the car. The design should allow for high fidelity sensing, redundancy and failover safety, with sufficient computing power and programmability to process software improvements for the life of the car. This is Hyperion 8, the architecture of 2024 models. The sensor suite is 12 cameras, 9 radars, 12 ultrasonics, and 1 front LiDAR. All of this is processed by 2 Orins. For the dev kit, we include Ampere GPUs to give plenty of performance headroom so that engineers can have the best environment to prototype new software. Hyperion 8 is available today. For anyone developing an AV or sensors for AV, Hyperion 8 is an ideal platform. We collect petabytes of road data from around the world and have some 3,000 trained labelers creating training data. Still, synthetic data generation is a cornerstone of our data strategy. Here you see a scene through the simulated surround cameras, with data labeled automatically. and on the right, some of the AI models that were trained with the data. Drive Sim Replicator is a synthetic data generator for autonomous vehicles and is built on Omniverse. The lens models are simulated and consider motion blur, rolling shutter, LED flicker, and Doppler effect. We work closely with sensor makers to accurately model their sensors. The camera, radar, and LiDAR sensor models are path traced. The materials are physically simulated for accurate beam reflections. We built a LiDAR materials library, and now we're also building a radar materials library. Replicator is a game changer for us. Replicator bootstraps the AI labeling tools and the AI models before Hyperion 8 is even built and any data has been collected. Replicator can label ground truth in ways that humans cannot, tracking moving objects across sensors, velocity, distance, occlusion, severe weather conditions. It is accurate and low cost, and it augments data where we have known gaps. Mapping is a critical pillar of driving. It is the collective memory of the fleet and can be considered another sensor. A couple of months ago, we welcomed DeepMap to our company. DeepMap is a world-leading expert in mapping for autonomous driving. Between DeepMap and our existing map team, we're scaling out globally. We do both survey mapping and fleet mapping. Fleet mapping crowdsources, or with one car, incrementally builds up a drivable map. With each drive, more of the route is perceived and reconstructed in 3D. Survey mapping is a fleet dedicated to mapping. We will have a fleet to survey map the most popular areas in the world. Survey maps prime the fleet even before it's launched. It also serves as the ground truth data for our cloud mapping AI system. Since the last GTC, we've turned on urban driving and autonomous parking. We're now running Hyperion 8 sensors, 4D perception, deep learning-based multi-sensor fusion, feature tracking, and a new planning engine. This is our Mercedes Hyperion 8, driving a route of urban streets and highways near our headquarters. You will see Mercedes negotiate merges, crosswalks, intersections, a roundabout, a cloverleaf, merge contenders, cut-ins, and pedestrians. Enjoy. AV will revolutionize how cars drive and will greatly improve road safety. The inside of the car will also be revolutionized. The technology of Maxine will reimagine how we interact with our cars. With Maxine, your car will become a concierge. Maxine will show you what is on the mind of the chauffeur precisely and use neural graphics to reconstruct a 3D surround view so that you can have confidence in the autonomous driving. Maxine will summon valet mode, search for a parking spot, and park the car. And Maxine, with all the amazing avatar technologies we're building, will seem incredibly smart.
What kind of driving modes do you have?
I have Max Range, Super Hush, Sport, and Super Sport. Which would you like?
I don't want to be late. Let's go Super Sport.
Got it. Super Sport it is.
All of this will run on the new Orin robotics chip. Future cars will be your personal AI chauffeur and AI concierge. The technologies I've shown you today make all this possible. Here we've applied it to autonomous vehicles, but the technology can be generalized to all kinds of robotic applications. A robotic stack for navigation and manipulation, and a robotic stack for human interaction. It's going to be pretty darn amazing. We covered a lot today. Let me put it together for you. Accelerated computing launched modern AI, and the waves it started are coming to science and the world's industries. It starts with 3 chips: GPU, CPU, and DPU. And systems: DGX, HGX, EGX, RTX, and AGX that span from cloud to the edge. 150 acceleration libraries for 3 million developers, from graphics, AI, sciences, to robotics, serving $100 trillion of industries. Nvidia accelerated computing is a full stack, data center scale, and open platform. Quantum 2 is the most advanced networking platform ever built, and with BlueField 3, welcomes cloud-native supercomputing. Cybersecurity is a top threat of companies and nations. We announced a 3-pillar zero trust framework. BlueField isolates applications from infrastructure. DOCA 1.2 enables next-generation distributed firewalls. And Morpheus, assuming the intruder is already inside, uses the superpowers of accelerated computing and deep learning to detect intruder activities. We introduced new deep learning frameworks. Nemo Megatron trains large language models. LLMs will be the biggest mainstream HPC applications ever. Graphs can now be projected into DNN frameworks. And Nvidia Modulus builds and trains physics-informed machine learning models that can learn and obey the laws of physics. GPU acceleration, data center scale, and physics-informed machine learning will give us million-x speedups and revolutionize drug discovery and climate science. Triton, an inference server for all workloads, now inferences forest models and does multi-GPU, multi-node inference for large language models. We introduced many exciting new libraries. Reopt for the $10 trillion logistics industry. cuQuantum to accelerate quantum computing research. cuNumeric to accelerate NumPy for millions in the Python community. The next wave of AI is enterprise and industrial edge, where AI will automate at the point of action. We offer several edge robotics application frameworks: Metropolis, the new Clara Holoscan, Isaac, and Drive. We highlighted 3 important technologies needed to enable edge AI: Unified Computing Framework, the new Maxine, and Omniverse. NVIDIA Unified Computing Framework is built for robotics applications. Edge applications are different than cloud. They stream sensors, do signal or physics processing, AI inference, speech, computer graphics, all in real time. Clara Holoscan, built with UCF, is a new software-defined medical instruments platform and runs in the data center or Orin, our new super-fast robotics processor. The new Maxine is an avatar platform. Maxine connects computer vision, Riva speech AI, and avatar animation and graphics into a real-time conversational robot. Our Metropolis engineers use Maxine to create Tokyo, a smart kiosk application, a talking kiosk. This will be useful for smart retail, drive-thrus, and customer service. Our drive engineers use Maxine to create Concierge. You can imagine Maxine being integrated into future Isaac and Clara Holoscan applications. Another demo showed Maxine as a video conferencing avatar, doing simultaneous multi-language conferencing. And Omniverse, our virtual world simulation engine, was a common thread throughout our entire keynote. Robots, autonomous vehicle fleets, warehouses, factories, industrial plants, and whole cities will be created, trained, and operated in Omniverse digital twins. I have one more announcement. We will build a digital twin to simulate and predict climate change. The last supercomputer we built was called Cambridge 1, or C1. This new supercomputer will be E2, Earth 2, the digital twin of Earth, running Modulus created AI physics at million X speeds in Omniverse. All the technologies we've invented up to this moment are needed to make Earth 2 possible. I can't imagine a greater and more important use. See you next time.
What are the greatest?
The greatest are those who are kind to others.